Thanks, Brad.
All right, guys. I'm Brad Larson. I'm from Coinbase, and I'll be talking today about how we're building a secure deployment pipeline. And I'll start off a little about Coinbase for those that aren't familiar. So Coinbase is a leading digital currency company with a couple of primary products. We let customers buy and sell Bitcoin and Ethereum on Coinbase.com, or trade Bitcoin, Ethereum, and Litecoin on our exchange, GDAX.com. We also securely store customers' digital currency, provide wallet features like send and receive. And last, we provide payment processing so that merchants can accept Bitcoin for payments. And for that wallet side, right now, Coinbase stores about 10% of all Bitcoins in circulation, which, look at this graph here, shows the value of all Bitcoin in circulation has risen steadily over the last couple of years, around $20 billion today, which means Coinbase is storing $2 billion, what amounts to digital cash. And as you can imagine, that makes exchanges like Coinbase a large target for hackers. Here are 4 of the more prominent hacks that have happened in the last couple of years. Mt. Gox, Bitfinex, Bitstamp, you may have heard of those. In these 4 incidents, hackers got away with what amounts to today $1.3 billion. So if you look at some of the causes for around 43 incidents that are cryptocurrency related, they kind of span the gamut from server breaches to app vulnerabilities to social engineering or insider jobs. And so we always have to be vigilant on security and make sure we're keeping the hackers out. And so security is always kind of baked into everything we do at Coinbase, which leaves us the problem because we need to keep the hackers out while keeping the engineers happy. And I think there's often a trade-off between security and usability. If no engineer can do anything, you're very secure, but they're very unhappy. And if they can do anything, they're pretty happy, but you're probably pretty unsecure. And so at Coinbase, we start by thinking, okay, we have this problem, how can we solve it securely? And then we go ahead and build it. And this kind of leads into how we work as a team, the infrastructure team at Coinbase. And so our mission is to provide self-service tooling that empower the engineer to rapidly build, ship, and operate services with low risk. So as much as possible, we want engineers to have full control, but so they only can do safe things. And so how do we do that? What's our approach to deployments? Today I'm going to talk about our kind of internal deployment tool called CodeFlow and some of the choices we made behind that. So it'll start off with a well-defined path to production, and it'll lead into low-risk deploys. And so a well-defined path to production. A simple way to increase the security of your infrastructure is to limit the choices that your engineers can make. The fewer choices there are, the fewer attack vectors you have to defend against. And so we've kind of settled on a number of conventions that we think help guide our engineers towards security by default. So here's a screenshot of CodeFlow, our internal deployment tool. And this is the path to production or path to deployment at Coinbase. It's basically a wrapper on GitHub and AWS with a little bit of magic internet money sprinkled on top. And it really organizes our services and exposes the information and settings needed to deploy services into the cloud. And so at Coinbase, all our services kind of start off as a 12-factor application that runs on a Docker container. And so the 12-factor app is a set of best practices for deploying applications in the cloud, kind of popularized by Heroku. And Docker, as you're probably familiar, is a containerization service that lets you kind of abstract away the underlying hardware and focus on writing code. And so running our apps inside Docker containers actually helps quite a bit. It works pretty well with the 12-factor app paradigm, because for the most part, our engineers only need to worry about the code base and the configuration. And then the rest of the factors like logging, port binding, concurrency are handled either as a consequence of using Docker or provided by our infra team. And at Coinbase, all of these services are run in AWS in a private cloud. And so once an engineer has an idea for a service, they need a GitHub repository. So they're going to create the repository, and there's a number of files they kind of need to make it all work. The first is a codeflow.yaml file. This kind of provides the settings for CodeFlow to deploy. Things like number of reviews required and some other information about the repository. They also need a Docker file which kind of specifies the external software dependencies their service needs to run. Then we have a Docker compose file which does orchestration and kind of specifies what services should be started in each deployment. And we have a .env file which specifies all the secrets that they may need or things that may change between deployments. Then we have the application code and our tests. And here we're using enterprise deployment of GitHub for enhanced security and control. And so once they have this kind of repository, what CodeFlow does, it kind of commits to the master branch main repository to a deployable code bundle. And it also exposes the deployment settings for each repository. And so there are three main kind of settings that any engineer needs to provide in order to make a deployment happen. The first is the service config. And this kind of maps directly to the Docker Compose file and actually follows the same syntax. And it is where the engineer specifies what services will be started for each deployment, what's the command to start it, what port to expose, and that kind of thing. And typically, each container is started on its own instance. So there's a 1-to-1 ratio between container and instance. And this provides some nice isolation, as we don't have to worry about privilege escalation or that kind of thing. It actually makes it easy to roll hardware if there's an underlying problem with that hardware. And you'll also notice that we have this kind of label of service group, which lets you kind of group containers on the same instance if need be, because sometimes that needs to happen, or it is for kind of cost-saving purposes. The next thing we provide is environment variables. And these are things like your third-party integrations, database credentials, API keys, that sort of thing. It's organized as a key value store with the ability to add comments. And these are typically used to note why and when an environment variable changed. When the service is deployed, all these envars will be injected into containers so they can be accessed by the code. Secrets are always encrypted at rest, so they're encrypted going into the database and unencrypted on the way out, and they're never otherwise stored unencrypted. The last option that engineers need to provide is the AWS config. And this lets engineers specify details about the actual hardware that will be running their service. Most of these variables, like instance type, ELB, or AMI, have default values, which makes it easier for an engineer to get started, because they only provide the ones that are different. You'll also notice that we have some rudimentary support for auto-scaling. So you can set min size, max size, and not shown here, but you can also add rules to scale up or down in response to traffic, CPU usage, or load on the database. And so once an engineer is ready to deploy a service and they've mastered a little bit of Git, a little bit of Docker, a little bit of AWS, and some environment variables, they can kind of deploy their service into our cloud in 2 clicks. Once to say, yes, I want to deploy, and then once to say, yes, I'm really sure I want to deploy. And after that, it's going to be queued, deployed to production, and then eventually done. Depending on how complex that service is, these deployments take between a minute to up to 10 minutes. Depending on how much steps need to start, the migration can be done, that kind of thing. And so this makes it really easy for engineers to take their projects and their ideas from concept to reality and start testing immediately in a production type environment. And I think there's only a few things you really need to touch. So it's pretty easy to kind of grasp all that knowledge and take it. We can expect every engineer to kind of know all those basic things. And so that's kind of a high-level overview of how engineers interact with CodeFlow. And now I'd like to walk you through kind of the behind-the-scenes decisions that help make that deployment secure. And so one of the things we strive for is this concept of low-risk deploys. And for us, that means that we want every engineer in our company to feel confident clicking that deploy button for any repository at any time. In fact, we're so confident in our low-risk deploys that we deploy CodeFlow with CodeFlow. And the way we measure that, albeit a bit indirectly, is the concept of deploys per person per week. We think this is a good metric because it scales, kind of regardless of team size, and it also is kind of a measure of the team's velocity. And we want this number to be as high as possible. The higher the engineering team's velocity is, the more deploys we're doing, the faster it's get code in production, and the faster our teams are moving in general. And I think it's a good sign of the health of the engineering team. At this graph, you can see we're around 7 deploys per engineer per week. I think that's pretty good. There's obviously an upper limit to how high this metric can go, but we think it's a good sign of how easy it is to deploy and how confident engineers are in deploying. I will give credit where this is due. We did borrow this metric from the Puppet State of DevOps report, and they thought it was highly correlated with those teams that kind of are higher performing. And so the first thing we do, kind of the foundation for our low-risk deploys, is we have a single AMI. An AMI is an Amazon machine image. You can think of this as kind of like the copy from which all other instances are started from. And we're using a version of CoreOS Linux, which is kind of a stripped down version of Linux, basically designed specifically for running Docker containers. So it doesn't have a lot of the extra libraries that something like a normal distribution of Ubuntu would have. Instead, those dependencies are installed via the container. And this has a number of benefits. One, smaller images equal faster boot times. Two, these stripped down images have fewer attack vectors. Again, fewer options equals fewer attack vectors. And finally, less maintenance, which is a big reason. We update our AMI every 90 days, once a quarter. And so that process of creating a new AMI and updating it across all of our services means it's much easier with just one rather than a bunch. It also means that all of our services are patched and updated and checked to make sure they're up to date every 90 days. And our security team only has to worry about securing one image. So this kind of all stems from the fact that fewer options are better. The layer on top of that, the layer on top of the base image, are our base containers. And so for every language we support at Coinbase, we have a base container that's, again, then stress tested by our security team. And you'll notice that we've only got a couple languages here. We've got a base kind of Ubuntu shell, we've got Ruby and Node, our primary languages. We've got a couple for special services in Go, Java, and Python. And so every service at Coinbase is going to descend from one of these base containers. So again, making sure that they're starting from this spot that's been stress tested by security, kind of guaranteed to be up to date. This means that, let's say, a new Heartbleed comes out, or some library has an issue. We can quickly update our base container here, and then update all downstream containers. These images are hosted in an internal image registry. We're using Key, which again is a CoreOS product. And so the layer on top of these base containers is the actual application code that engineers are writing. And we need to secure this somehow. And the way we do this is we make heavy use of consensus. Consensus lets us give narrow sets of permission to more users. And helps reduce these single points of failure where there's only one person who could approve a change or that kind of thing. And the main two places we use consensus are proposing changes to the code base and proposing changes to the deployment configuration, things like environment variables or AWS config. And so when a change is proposed, we require reviews and approvals from other engineers before that change is applied. So here I have the codiflow.yaml file. And Heimdall is our internal consensus service that kind of monitors everything, making sure that we have the required reviews, everything is kind of hunky-dory, kosher. And so the two things I'm exposing here are record reviews, which kind of says how many engineers need to approve a change before it's kind of enacted. The second one is requires MFA. For really sensitive stuff, repositories, we could possibly access customer funds or code flow itself, where we could affect all deployments. We require a dual push to the engineer's phone to have a second kind of factor authentication for each of these approvals and reviews. And so this kind of helps us protect against any possible consensus forgery attacks. We have kind of greater trust and confidence that our reviews are coming from the engineer that it says it is. And so if you look at this in action for a change to our configuration settings, whenever you change it, it's going to stage that change and then let engineers know that there's a pending change. And then you also either approve or reject it. And these change sets have a couple precautions built in to, again, enforce security. We make sure that the user has the right permissions to view this change set. So we usually limit these change sets to engineers that are working on that project or a maintainer of it. And you kind of set some rules. For really sensitive repositories, we actually have a special list of who can kind of view changes. We also make sure you can't vote for a change that you created, that you can't vote twice, that you can't vote, you can only vote for pending change sets. That is, you can't take a change that was rejected and make it approved. And we also lock deploys while there are pending changes, such that if you do need to get a new API key out there really quickly, once you propose that, no one else can deploy over the top of you. On the code base side, Heimdall, our consensus service, kind of monitors every commit to that repository and is constantly checking, does this commit have the required number of reviews? Once an engineer comments +1 or looks good to me, Heimdall will comment and say, you're good to go, you can merge this to master. But you'll notice we've got a couple other checks that are also run automatically every time an engineer commits to a repository. Salus is our internal security tool, and it does two things. It's going to scan all our code for stack analysis, so looking for CVEs or that kind of thing. We also have a shadow scan, which is checking to make sure that your code's kind of conforming with our security policies. And last, we have our Circle CI integration testing, or automatic tests. And these are run every time a commit is made. Once an engineer has merged that to master, we're going to run the same 4 checks once again to make sure that nothing has changed since you branched off, make sure you rebase correctly, that kind of thing, make sure we didn't miss anything. And only once those 4 checks have passed a second time can you deploy that commit. We're also, when you commit to master, we're going to build that image. So we're going to take the Docker file and try and build it to make sure nothing has changed or like everything is still valid. If that build fails, you can't deploy. And so these 4 checks and this consensus kind of operation give us confidence that even though engineers are making changes, that someone's reviewed it and we're pretty confident there's no glaring security holes in that code before it's going to production. We also monitor for ways engineers could get code into production sneakily. So I'm sure it's happened to you where you accidentally committed to the master branch. Well, Heimel's going to watch for that as well. If that happens, we're going to create an issue in the repository, and again, we're going to lock deploys. So Heimel's always enforcing that every commit that goes out to be deployed has been reviewed by the appropriate numbers of engineers. And lastly, we provide the option to lock deploys. Because we want everyone to feel confident in that deploy button, we give engineers the option to lock deploys. Because there's going to be times when you don't want anyone to deploy. Let's say there's a migration in progress, or it's Friday and everyone's at a happy hour, or it's the holiday and there's no one at a computer, just you. So we built in this locking mechanism to let engineers kind of prevent deployments. And anyone can lock for any reason. It's very easy. And this is so that engineers feel empowered to take care of this kind of deployment thing and make it sacrosanct. That you should always be able to deploy, and if you can't, well, then we're going to tell you you can't. The last thing we really kind of do is we try and make information about each deploy as accessible as possible. So for any deploy, we're going to expose logs coming up from that container. We're also going to expose server details, so the actual hardware that's running on. We're going to expose stats about utilization, so CPU, traffic, that kind of thing, as well as all the raw traffic metrics. We'll also expose links to the bug tracker so that you can easily kind of correlate things like, did this bug happen with a new deploy? And our philosophy here is the more information you can easily expose in one spot, the easier it is for engineers to diagnose problems and respond quickly. And the more likely they are to use this kind of tool. And when deploys do fail, because they inevitably will, where it's a combination of bad luck, hardware, or software failures, we make sure that engineers have easy access to the logs, and they should hopefully tell the engineers something about why that deploy failed, and if they need to fix that issue before they try to deploy again. The last thing we kind of do here is this concept of immutable infrastructure and blue-green deploys. So at Coinbase, we're never going to modify an existing container and try and update the code running on that container. We're always going to deploy over the top of it and then spin it down. So this is a big reason why our deploys are so low risk. Because every time we make a deployment, we have an additional check that says, have these boxes come up, either responding to our health checks, and if everything looks A-OK again, then we'll finally switch it over. But if it doesn't, then we'll leave the old deployment still running. And so this kind of allows for these zero downtime deploys and really keeps us low risk. And so with this kind of blue-green deployment, there's kind of 4 steps. The first is going to be creating a new ASG. And so we're going to wait for that to come up. And once that happens, we're going to wait for all the instances to come up as well. Once they're up, we're going to wait for all the health checks to start working. And once all the health checks pass, then we're going to detach the old ASG from the ELB and attach the new one. And that kind of process has been complete. So that's kind of the high-level view of how we keep our code secure and what we're doing in order to do that. That's all I've got. If you want to know more, you can check out engineering.coinbase.com or blog.coinbase.com. A number of my colleagues have written about other things we do to keep security top of mind and how we do some stuff. Coinbase is always looking for good engineers. Talk to me afterwards if you're interested.
Thanks, Brad. Questions for Brad?
Are you using ECS?
No. The container service? We've got our own key, which builds or stores our images.
Question over there, you'll have to shout, we've only got one mic.
How do you do rollbacks?
Well, you just deploy a previous commit. So let me see if I can. So you can click on any of these commits here, and that would bring up the ability to deploy that commit. We have some rules in place where you can't deploy really old code, or you can't deploy commits that are so far off ahead of master. But it's pretty easy to roll back, because you just, like one before that, deploy at the top again.
How much of your stuff is open sourced in these tooling?
Some stuff, we've got a tool called GeoEngineer, which we use for a lot of our Terraform and coding infrastructure. We're in the process of open sourcing CodeFlow with a goal of having that done by the end of Q4. Fingers crossed.
Anyone in the back?
Is there any reason related to security or something else why you didn't choose to go for a container management system such as Kubernetes?
The main thing why we built CodeFlow was we didn't find a compelling answer to that consensus problem. We wanted to have consensus a big part of our system where we have multiple reviews and we have multiple reviews that configuration changes. So we could find stuff like ECS for container management or deploying, but it wasn't like CodeFlow kind of brings everything together, and then the real special sauce is that consensus on top.
Anyone over here?
Yeah, I want to ask, what is your branching strategy? Is it feature branches and then pull request to master and then it gets deployed?
Exactly.
That was an easy one. One more. All done, going once, going twice. Thank you, Brad.